Hello, legends. This is Mr. Maze coming to you through the digital space. So excited to share with you a little bit of wonder. It's morning here. I'm actually in my office prepping before school starts, and I am here to give you a little bit of magic. So if you'll take a look, we're messing about with 5.3 today, and 5.3 is most specifically a look into sampling means. So we've worked with sampling proportions, and now it's time to start talking about how means work in that same space. Now, as we know, the way that things function with sampling proportions shares some things with sampling means. Similar to sampling proportions, sampling means are a bunch of small samples, all of the same size, right? Very important to have that in your mind and in your awareness. And those same size samples come together to make a distribution, right? So if you imagine a distribution, I'm going to call it a fairly normal one, and we'll learn how we determine that soon. And there's some demarcations on the x-axis, and each one of them represents a value. And above them sit a bunch of dots, or histograms are normally used with quantitative data, aka the data we normally use with means. And those dots, each one of those dots might represent a sample size, n equals 30 or something like that. You give it a value. And each one of those is a sample of that amount, and then each one of them has a sample mean, okay? Now, before I go into some more detail, I hope that overall overarching picture makes sense to you. And I want to go over two quick rules. One of them is a rule that is applicable to means and to proportions, and one is a reminder for your proportions. So something that has to do with 5.2 that I really want to hammer home. The first one I want to go over is the 10% rule. That applies to all sampling distributions, proportions and means, right? Does not matter which, both are important. Or it is important to both, I should say. Obviously, both are important. We wouldn't be doing the brilliant study of statistics if both weren't important. The 10% rule is to make sure your sample is less than 10% of the total population. And if you're with me on slide 3 of the 5.3 sampling means slideshow, that's what the rule says. Make sure that your sample size, right, so n, right, is less than 10% of the total population, p. And the reason we do this is so that we can ensure independence. And that is a prerequisite to treating things as if they are treated as normally distributed and other things. Now, be aware, it is not the only way that we determine if we can do our wonderful normal calculations and things of that nature. What this is specifically ensuring is independence, and as we know in this class, independence is important to just about every calculation we do because we're in Stats 101 essentially, and in Intro College Stats, we do a lot of independence-related calculations. Independence allows for dependent elements, things that we can't control for, that we need to know the facts about, to not come into play, right? So no other interrelationships between our variables or our measurements that could cause us to have to do extra calculations. Okay, so that is the 10% rule. Know it, live it, love it, and know that it applies to means and proportions. Very important, okay? Now, the other one is the law of large counts, or the large counts rule. That, of course, applies only to proportions. So I'm being a little silly putting it at the start of our means video, but I did want to go over it one more time. The large counts rule simply states that in order to use normal calculations or treat proportions or sampling proportions specifically as if they are normal, you must check that n times p and n times 1 minus p. So the number in your sample times the probability of success and the probability of failure, both must be. Both must be. Look at me. Both must be. Both must be greater than or equal to 10. And all that's saying is I need at least 10 people that are failures and 10 people that are successes in your measurement. So if I found that 50% of left-handed people and 50% of right-handed people responded a certain way, and I was just seeing what's the proportion of left-handed to right-handed people, I would need at least 10 left-handed and 10 right-handed people. Even if it's, only 2% of the population is left-handed, which I don't think that's accurate, but like pick a small number. Even if that's the case, like let's say it's really small, you still need minimum 10 for each. Okay, and that's the large counts rule. And that's all on slide 3. All right, we've done our class prep. We've done all our work there. Note, please, that 4 through 7 are the slides that allow you to go through the homework for 5.2. Please know it, live it, understand it. On slide 9, we explain the same thing I explained at the very start of this presentation, this little video notes lecture for you, which is just that we have a bunch of sample means. Remember that X with a line over it, X bar, is the term for sample mean. So let's say I have an n amount, right? Let's say it equals 30, and I have a sample of 30 different heights. The X bar would be the mean for a single sample of 30, right? Where each one of those X bars has a value, and the center of the entire distribution of different sample means going across, this center here would be our true population mean. And that's what we call this. And so as we see on slide 10, we have 2 equations. We need to get really used to our different calculations for parameters. And the 2 here are the population, the mean of the sampling distribution is the population mean. We treat those as the same. And this is very similar to what we do with population proportions, right? The mean of the sampling proportions is equal to the true population proportion. We act as if. And therefore, the mean of all of your sample means, which is what I'm kind of suggesting here, is going to be equal to the true population mean, right? That pie in the sky value. So if I do a bunch of samples of 30 people to see what their average height is, and I get a height of around 5'9", as my average height in my 30-person sample. And then I run many of those samples over and over and over and over and over again. And then I average those out. I would then expect to find a mean of those means. And that mean of those means is what I would treat as my true population proportion. True population mean. The other thing I have here is an equation for standard deviation, right? Now, one thing I want you to catch here that's a little bit hard to note at first, but that we will get used to for specifically the standard deviation of means and mean sampling distributions, is that this says, and we need to get this through our brilliant minds, the standard deviation of your sampling distribution, right, of your mean of your sampling distribution, is equal to the true standard deviation that you've calculated, the true pie in the sky value, divided by the square root of n. And so I want to go through for a second and show you what that looks like. If you take a look at slide 11 and slide 12, I have a walkthrough for an answer on this, and I want to go through it. So for example, on slide 11, we see, I'm going to go to green for this. If a sampling distribution of 100 randomly selected items has a standard deviation of 15, then the standard deviation of the population is. Now the values I need to note here, are 100. 100, of course, is our n value, the number of people in our sample. Remember that n is always the size of your sample. And in this case, our sampling distribution is 100 selected items, right? Those items will be your size n, your sample size n. We are then plugging that into the formula, but what you need to note here is the standard deviation of your n, right? So the standard deviation of n is the thing that's going to be on the left here, right? So our equation is actually 15 is going to be the standard deviation for your sample mean. So 15 equals our true standard deviation for the population over the square root of 100. And that yields a value of 150. Ooh, see how I wrote that? What was going on with that, Mr. Mays? That's the most hideous 150 I've ever seen in my life. Okay, and I have a great Aunt Wilma. No, I'm just kidding. Could you imagine that? That would be hilarious if she made it to 150. I don't think anyone has, but that's projected to be the maximum human age we could bring someone to. We'll see if it ever works. Okay, so the thing that I really wanted to hammer home there is that the mean on the standard deviation on the left is the standard deviation for whatever your n value is, right? Your sample standard deviation is on the left, and on the right is your true population standard deviation, beneath which you find the size of your sample. Okay, that's the majority of the bulk work we have to do here. The last thing I really want to push home is if you go to slide 13, we want to get really comfortable with how standard deviation changes based on sample size. So n and standard deviation. And it's the same across proportions as it is for means. So really quickly, I want to take a look at, for number 13, it says if a sample increases from 100, n goes, ooh, my goodness, once again, except this time I made an m instead of an n. N equals 100. That goes up to n equals 900. First thing to note, when it says up by a factor, that means we are multiplying. Okay, rule 1. If n goes up, then, of course, standard deviation goes down. And if n goes down, standard deviation, of course, goes up. That's the first rule. That I want you to know inside out and backwards. Why? As you sample more people in a particular sample, right? The bigger that sample is, the clearer the results will be, the more normalized the curve they will have, but also, and most importantly, the tighter, the lower the variance you will have. And of course, standard deviation is a measure of variance. So if the size n has gone up, the standard deviation will go down. If the size n has gone down, the standard deviation will go up. So we already know between answers A, B, C, and D that decreases is the right answer because we know that our sample size has gone up by a factor of 9 times. Therefore, our standard deviation needs to go down. And the rule of thumb is if n goes up blank amount, and actually, let me make it super clear. Here's the real phrasing. If n goes up by a factor of blank, standard deviation goes down I can't spell. Fix it. By a factor of 1 over, okay, and actually I'm going to give blank a variable. Let's just call it m for maze, giant M, okay, by a factor of some amount. Standard deviation goes down by a factor of 1 over square root of that amount. Okay, so in the case of the question on number 13, your sample has gone from 100, n equals 100, to n equals 900. That's a factor of 9. What do I do for that? No matter what it is, I do the old number underneath the new number, right? That's how I get a factor of 9. I take what I had, I make it the denominator. I take what I've gone to, and I make that the numerator. You do the exact same if it went down. If I said n went down by a factor, or went down from blank to blank, or decreases from blank to blank, I would be saying the standard deviation increases by a factor of, and I would do the flip-flop. In this case, our value m, whatever you want to call that, I'm just saying m because m is for Mays in this case. I should call it J for John, right? Jack Mays, or whatever. But we'll say m. And that's our factor that it's increasing by. Then, standard deviation then must decrease by 1 over the square root of m, which in this case is 9, which would be 1/3, which is why the answer is B. And the math behind that, fairly simple. Let me just do it over here. Standard deviation is impacted in this way for means. It's impacted in this way for proportions. And what you'll notice is the square root of n is always on the bottom. So if n goes up by an amount, whatever that amount is, it's under the square root and it's in the denominator. So that's going to affect the standard deviation, no matter what n is, by being 1 over the square root of whatever the change is to n. And you need to make sure that change is a factor, a multiplication, because as you can see, all of this is being multiplied. All right, and that holds true for means and proportions. Know that, live it, love it. All right, there are some practices here, but the last thing I need you to know are the two ways we determine if we can treat our means and our sampling distributions for means as if they are normal. And there are two rules. We're on slide 16 now. If the population distribution is normal, then the sampling distribution for means is normal. This is true always, always for any n amount. I could have n amount of any kind. Oh, again, my inability to scratch letters onto a virtual tablet fails me, or I guess betrays me. N amount of any kind. Still normal if and only if we are told the population distribution is approximately normal. So if I tell you that the distribution of the true population of elks is approximately normal, I've done a sampling distribution where the sample means of number of elk in a particular area are, or maybe not even number of elk. That's not fair, because that would be better done as a proportion. Well, you could do it. But let's say like average age of an elk, right? Let's say that's approximately normally distributed. Even if I have sample size of 4 elk that I'm sampling for my mean distribution of ages, and I'm making a bunch of distributions of 4 elk, or samples of 4 elk on a distribution, I would treat that as approximately normal because I know that the actual ages of elk are approximately normal. Okay, that's check one. That's one way. The other option is what's known as the central limit theorem. This is on slide 17, and this one is very easy for means. If n, your sample size, is greater than or equal to 30, we are good to go. As we go higher up in higher level statistics in our lives, not necessarily with me, but off when you go do greater and wonderful things with other teachers who are very fortunate to have you because you're a brilliant student. I know it. I teach you every day. You will find that this central limit theorem is flexible, and we end up using different amounts depending on the study that we go into. Sometimes it's a higher number. 100 is often used in some very exacting fields. But for our purposes, 30 will do, and this means we can treat it as normal, even if the population distribution is not normal. This is the central limit theorem. This is the equivalent of the large counts rule for proportions. This is specifically for means. This technically holds true for proportions, but you have to do the large counts theorem for proportions, so you're stuck with it. A very common sampling distribution question, and the last thing we go over today in these video notes, is on slide 18 and answered on slide 19. You will note that on slide 18 and on 19, the true population of college-educated adults' mean IQ is left skewed. However, we do samples where n equals 200 college-educated adults. Because we are doing a sample size, according to the central limit theorem, and this is true and wild but very cool for the way we do statistics, we treat our sampling distribution, right, of mean IQs. The distribution of sample means, we treat that as normal. So the answer is C, because we would find a mean of 115, which is given. We calculate our standard deviation. You'll note that we give the true population mean, and we give the true population proportion as being 15, so we'll do 15. And we know the amount in our sample is 300, so we'll do, 200. What a fool I am. What a fool. You're shouting at me, Mr. Mays, get it right, would you? 200, not 300. We put that as the denominator. We solve for our, it says what is the standard deviation for the sampling distribution. And that's what we would get. And of course, the answer there will be 1.061 or whatever that is. So our answer should be the one, answer C, that says mean of 115, standard deviation of 1.061. But then lo and behold, and this is very important, not left skewed, but normally distributed. Because according to our central limit theorem, no matter the size or shape, I should say, no matter the shape of the population, as long as the population is greater than 10% of the sample, we will treat the sampling distribution of that population as being normally distributed if n is greater than 200, but less than 10%. And we can assume that 200 people is less than 10% of all college-educated adults. Okay, go through, study these notes, know them inside out and backwards. Know that I adore you, I am looking out for you, I am proud of you, and I am elated to be your teacher. You've got this. Remember that statistics is such a beautiful and brilliant journey. It challenges us. It is critical thought in constant action. And be never discouraged, but try ever hard, okay? The more work you put in, the more brilliance you get back. And be aware that every time we make a mistake in statistics, we only ever learn more. This is Mr. Mays signing off.